Oh, what's up, everybody? Welcome back. Today I want to write a hash map. There's actually a reason. You come across this thing in school, they tell you how to do it, you never think of it again, and you say for the rest of your life, nobody ever has to write a hash map. We're doing it. It's finally happening. 10 years later, I finally have to write one. So, the problem is that a while ago, we kind of, wrote a, allocator system, I guess I'll say, where we kind of made it so that we can allocate memory and just forget about it. Fuck free. We never call free. We just allocate memory in batches and we clear the whole batch at once, right? And a way like that's like a very successful strategy overall. It really like reduces error handling cases and makes thinking about allocations a lot easier. You don't have to remember to free every individual thing. You just like at the top of like a block, like you get like an HTTP connection and you go block of memory, start here, and when the HTTP connection dies, nuke the block of memory, and you don't have to think about like anything in between there. You're just like, fuck it, if we over allocate a little bit, no big dealio, we'll get it later, right? And this strategy is like relatively successful. However, it's based off this concept of like linear allocations, right? So we kind of like have a chunk of memory, maybe growable, right? In some cases we allow growth of this thing, but like the general idea is that you have like a pointer to somewhere in the block of memory, and when you allocate, all you do is you just bump the pointer forward. Right, so you go like, I want some stuff. And so you're like, okay, you want this stuff? Here you go. Now the next guy who asks comes here, right? And then when you want to like free the block, all you have to do is like write down where the block of memory started, and you just go like, okay, bump, we're back here. Delete everything that we allocated in the future, right? Simple. The problem with this is is that like you don't like get to like free individual things anymore. So if you were to like allocate some more stuff, you go, okay, I want like a second thing over here. Boom. And if you're like, okay, I'm done with the first thing, this guy, I don't need him anymore. We don't really like support that, right? Because there's no way to like bump this arrow backwards in a way where you keep the second half but lose the first half, right? So the only thing you could do is just like hope to God that you finish with this second block within some reasonable amount of time, and then reset it all at once, right? This is fine, right? Except for the fact that there are like standard library containers that assume that free does something, right? Because like, why wouldn't it? It's a reasonable assumption that if you ask for the memory to be freed, it gets freed. Which means that like for something like a hash map, or let's start with like the simple case of just like a growable array. What they typically do is they allocate like a small amount. You go, I fill up this small amount, and they just like allocate a new amount chunk, copy the stuff in here, down here, and then delete the old chunk, right? And I believe, I didn't actually check this, but I assume that the standard library hash map kind of does like a similar thing, right? So you have like a small hash map at first, you go, oh shit, I've got too much stuff in my hash map, there are too many collisions, I gotta grow it. And so they just like allocate a new thing, delete the old one. So in the context of our linear allocator, what that means is every time the hash map grows, you have some like space that you wasted. Ew, gross, nasty. Arguably, it doesn't fucking matter, right? Most of the time, it's like you're just going to like delete that space anyways. But this has come up a couple times where we're doing like a lot of small hash maps in some area, and between like memory reclamation, which is fixable, but what would be kind of nice is if these hash maps were friendly to the idea of this like linear allocator. And so like the end goal here is probably to have a hash map where when he says, oh shit, ran out of memory, instead of copying to a new segment and deleting, instead, what if we just made a new segment and used both, right? Wow, now where we've grown, but we also didn't lose any of the previous memory, we're more storage efficient. Hell yeah, bing bang boom. So that's kind of like the end goal. Today, we're going to limit the problem statement though. And so instead of doing this, we're just going to try to make a hash map that never grows, right? So I want to make a fixed capacity hash map that says, when I like, give me some buffer of memory on start, maybe maybe it starts by only using some segment of this buffer because it might be better for cache locality if all of the elements in your hash map are close together. But maybe it just uses the whole thing, maybe. And the idea is that like it can grow up until the point where this buffer is full, and then it just says, nope, no more fucking growth, no more elements fit, we're out of memory. That's kind of the intent. And so to do this, I think we need to re-implement a hash map. And I think that's kind of like a fun little problem to do anyways, so we'll do it. We're finally lead coders, we're implementing a hash map from scratch. Let's go, baby. I've never done this. I kind of just like glanced at the Wikipedia page yesterday, and I think it's basically just like I like kind of read it at about this level of detail, you know, just kind of like slowly scrolling and looking for words that I can see. I think that it's basically what you would guess. Hand wavy, I think is what you would guess. So I think let's just kind of like make one and then see where it goes. There's a good chance that I'll do something fucking stupid, but it is what it is. It is what it is. I also think the goals here are not necessarily to be like the most efficient hash map, right? I think that the like, if we're in like an order of magnitude of like a good hash map, I'll be happy. That's kind of the plan. Okay, so make an interface. Make an interface. Hash map. This thing needs to do something where he's like, I guess you want to like have some sort of like key to value mapping, right? So I guess this needs to be a hash map in this language, is going to take in a key type and a value type. I think that makes sense. And he's going to return some sort of type. Let's go. Some zig link. I'll click it. Self-hosted x86 is now default in debug mode. Let's fucking go! I feel like I'm tight on time today, so I'm not going to look too much into that, but that looks fucking sick. I'm excited. Excited. I'll give that a look later. Okay, so how are we going to store this stuff? We said that we're going to get like one buffer, right? We're going to initialize this thing with a buffer. And, oopsie, what the fuck did I just do? I must have auto-completed something by mistake. And I guess this has to be a mutable buffer. And I guess for now, we're going to be like, buff is U8 slice. And I guess we just return that for now. I guess. I don't really know. Cool. Let's just say we are going to use key and value later, but we don't right now. And what are we kind of expecting this thing to do? We're kind of expecting that we go like, we have some map is a hash map where we are kind of going from like integer IDs to like strings or something, right? Something like this. And we want to initialize this with some buffer. So let's say that we have, you know, 4K of stuff that we can work with for hash map storage, which is quite a bit, to be honest. And then we're going to be like, I guess this needs to take this by reference or by pointer. And we're expecting to do something like put, you know, 10, 10, right? And we're putting 5, 5, and like, we're expecting to do like, I don't know, maybe like a get or put as well, right? We're expecting like something like this, and then we say like, if this thing was not there, this is kind of like the standard library interface, we can like say initialize this thing in some way, right? So we'll set it to 3. This is kind of like and maybe like a get on here as well. So we could maybe a get pointer and a get, but for now we say 5, and we're expecting this guy to return us the string, you know, this is supposed to be 5, right? That's what we're supposed to get back here. This is kind of like approximately what we're looking at. Let's skip the get or put for now and just look at get and put first. So put is going to be something where we take in self as a self, and we have like the fucking key type. In case you didn't know, you don't need the comp time annotation with the types. Yeah, that's true. I feel like that's just like a habit I got into because I saw it a lot. I think the standard library does that. I think that's like a common thing, right? They say comp time t here, so I'm just doing it because they do it. But you're right that you don't need it. I have run across that, but I'm just like, I don't know. I do what I do. key. I guess saying that these things have like real names is more reasonable, huh? Key and value is value. And this returns nothing? Sure. So these things are failable, I guess. And this is just unreachable for now, and we just say, I don't use these things. Okay, and then in terms of get, we are going to get from some key and return a value. And it's unreachable. Does it build? They're kind of hype. Error union is discarded. So I think get should return an optional, to be honest. Not an error. So it's like either the thing is there or it's not. And this builds, which is hype. And if we run this thing, zig build, and bin hash map test, we crash because we haven't actually fucking implemented anything yet. But I'd say that's a pretty big win. Pretty big win. Things are ready to move. So now the question is what do we do? So how are we going to store these things, right? The natural idea here is that you have some function hash, right? And this guy returns some index into some array, and you probably have some sort of limit on the size of this thing, right? So if we can fit like 10 elements, then you hope that this thing returns like a number between 1 and 10 with like uniform distribution for all possible inputs, right? That's kind of what you're hoping. And then all you have to do is you say like, this thing is probably like a buffer of value, maybe. And you just say, here, you go hash key, I guess. You know, key, any type or something. You like hash this thing and you just do like self buff at this location is equal to value, right? Now, the problem here is this Rust knows zig. Zig, zig, zig. The problem here is that if you have, you know, your buffer can store 10 elements, if you put in 100 numbers, at some point, they're going to collide, right? And if you just happen to pick the 10 numbers out of those 100 that collide, you're going to, like, hit a collision here. So we have to store something that's, like, not just the value, but, like, you need something that's, like, let's think about this. You need valid, right? So whether or not something is stored in here or like empty, right? Or you could just kind of store it like this. But then what happens if you hit a collision? You have to be able to like resolve that collision somehow. So skimming the Wikipedia article, if you happen to have like two guys that want to go into the same slot, they kind of just listed all of the ways that you would guess to do this collision resolution, right? One is like the one that was like most natural to me is like you just try the next slot, and then you try the next slot, you try the next slot. You just like move forwards until you find an empty one, which means that like you're maybe like pushing the problem into like another collision for someone else, right? It means that the next guy who tries to hit, like if this slot's open here, then you store your guy here, but then what happens if somebody tries to hit this? Well, then he's got to kind of move forwards as well, right? So it kind of like propagates the problem, maybe not so great, but is kind of good for like cache locality, right? It's really easy to search forward a few times because the computer will be like, "Ooh, that shit's in cache, yum, 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 yum," right? Another thing people might do is you might do something like where you have this guy is allocated, you hit him, and you go, "Uh-oh, there's, you know, problem," and, you know, you might just like store a linked list of all of the guys you've collided with, right? So you just kind of like loop through these like linked lists until you find more. Another one that they talked about was each one of these slots is actually like another hash map, right? So like this is just a pointer to another hash map, and then you just keep going on these hash maps until like there's no more collisions, right? So I guess that means that like probably the hash function uses like different sizes and stuff, and you just kind of like, I don't know, something like that. What else did they say? They also said there was other ones in here. Oh, sure, you might do something where you like this linear gap thing. You might, instead of like storing with the adjacent node, you might like jump forwards by some like fixed increment, right? Basically, you just need somewhere to put it, right? Put it somewhere else on collision, right? So I think I'll probably start with this one where we kind of just like scan forwards because that seems relatively simple to me. But we'll see how that works. Now, probably just like for like computers to feel happy, I assume that you want to store kind of like whether or not things are valid, kind of like out of band from the values themselves. I kind of assume that you want like key storage, value storage, and then like metadata storage. I assume that you kind of want these separately. Maybe? And then you can kind of like inject the key and value into like the same indexed slot in these. I'm not sure that makes sense. It probably depends on like how usage of this thing is going to go, right? Like you're going to be iterating keys and values sometimes, right? When you return, oh, it's actually probably not true. It's probably not true. So when I like return like an iterator where I iterate over all entries of the map, that probably is going to come from like metadata, where you just kind of like loop over the whole array and check if things are set or not. Maybe there's probably some more optimized way to do that, where you like track somewhere else which ones are valid. But if you maybe made sure that your available area of this guy was always within some reasonable size, like reasonable ratio of how many elements are actually stored, right? Make sure you're only storing things in the bottom 8 elements if you have like 1, and then only in like the bottom 20 if you have 10 type shit. Then maybe just like hard looping over everything is like kind of fine. So yeah, let's assume that. And then in terms of metadata, do you really need anything other than like valid? Maybe. Maybe not. It kind of feels like it's the only thing I care about is if this element is populated or not. That's how it feels. Which means you only need 1 bit of data for each slot? Right? Maybe? Which sounds kind of like stud dynamic bit set, except this thing is... yeah, probably. Sure. Okay. That seems reasonable. So, what we need to do is we need to take this buffer of U8s and turn it into this stuff. Okay? So I guess that means that we can kind of have like an allocator in here. Maybe we don't need it. We only need this at the beginning, maybe? So we could do like std heap fixed buffer allocator from this buffer. And we just need to like calculate the sizes of these things appropriately. Probably. Right? So we probably have like the size of the key. We have the value size. And we have like the metadata size is fixed. I think. And we need to like construct some number of allocations here so that this stuff fits, I assume. Right? So we need to do like, my brain, it hurts. So we need like num elms that fit into this guy is like something along the lines of this. So we have like buff size, we have key size, value size, and metadata size I think is fixed if all like This is just like valid. Maybe. So this is going to be like, you have some size plus alignment. I think it's better to use the types here, actually. I think. We'll probably have like, this is interesting. We'll figure this out. So, key type, this is key like this. Value is also a type. Okay. Oopsies, comp time. Someone in chat, you don't have to write comp time. I know. But I'm going to anyways. So, I guess we want to, like, there's something about alignment here where like this buffer is not necessarily aligned to where these guys can come from. So you kind of need to split it up where you, let's deal with that later. So let's pretend the buffer is aligned. It's not, but we'll pretend, right? In this scenario, what is the function here? It's like n times key size plus n times value size plus n times 1/8, right? Because we can have 8 bits per byte in the valid area. So plus n over 8 is equal to bufflen, right? Now this is not going to work perfectly, but we can start here. So this turns into n times key size plus value size plus 1 over 8 equals bufflen, right? So that means we have like bufflen. If we were trying to get n, then we divide bufflen by all this stuff. N equals, let's just do this. N equals bufflen over this stuff. Now, this doesn't work with integer math, though, because 1 over 8's a no-go. So, can we restructure this so that it does work? Can we? I mean, we could say, if we multiply this, like this, then it becomes this. Does it? Am I crazy? Hold on. So if we multiply both sides by 8, 8n, 8n, plus 8n over 8 is equal to 8 times bufflen. Then we can kind of shuffle this around. So this becomes 8n is equal to this is equal to 8 times bufflen, right? Then we shuffle this around, so it's like 8n is equal to 8 times bufflen divided by key size plus value size plus 1, right? And then we have n is equal to, yeah, I think that's right. So then we just need to divide this by 8. Right? Which looks like it cancels out, but then you just do this in the right order so that it works. I think. Am I stupid? Integer math is hard, man. I think that it's right. 8 times bufflen over key size plus value size plus 1. Divided by 8? I think that's right. And this will floor? Okay, I don't know, man. This feels kind of right. We'll see. Now, this is also what we can do here to deal with the alignment is we just subtract bufflen is equal to bufflen minus a line of key minus a line of value, which is like quick and dirty hack to avoid alignment making us be too big. So we'll just waste one. That's fine. And then we'll say, do some 8 times, then divide by 8 so that there isn't a 1, 8 in the denominator. I don't know, man. In line 10, you factor out an 8n, but you only have n. Oh yeah, true. True, that is just wrong, huh? So it's actually like this. That's a good point. I'm a dumbass. Oh no, wait, this is right. Because this becomes like this, right? The 8n over... Oh, yeah. You're right. So it's actually like this. Which means that we have to get a little smarter with the math. Jesus Christ, is that not trivial to solve anymore? Yeah, it does seem kind of hard, huh? Does this work? Does this work? You have 8n. Is this okay? Let's just ask Wolfram Alpha to solve this for me. I'm not seeing it, obviously. I just want to make sure. I'm not sure if this turns into like a quadratic or something. It shouldn't, right? an plus n equals this. Solve for n. Oh yeah. Cool. Oh, of course. I'm a dumbass. Of course. So then you just, you say, I'm a dumbass. So we just pull at the n here instead of the 8n, like a dumbass. 8 times here. God, I'm stupid. Math is hard, man. It's like this. And then you have n equals to buff len over 8 times key size plus 8 times value size plus 1. Thank you, whoever pointed out that I just heavily fucked that up. Thank you. Math do be annoying sometimes. Yeah, they always get me with that shit. Cool. Cool. I think that makes sense. Okay, so now we should have, num elms is num elms given buff key and value. Okay, and so we should be able to be like, key storage is allocate. It shouldn't matter what order, so we should say order would matter if alignment, if we did smart alignment packing, packing based on alignment. We don't. But we don't smile. Okay, so we allocate num elms keys, we allocate num elms values, and we allocate stud dynamic bit set. Unmanaged seems reasonable. And then this probably we need to edit. how the fuck do you use this guy? Resize? New length? Fill? Yeah. Nice. So we just say, what was it a thing? Allocator? Oh, this is wrong, by the way. FBA is like this, and then the allocator is the FBA allocator. Boom. Boom. Okay. And we fill this thing with everything is invalid at first. We have no elements in here. So now we should be able to return like key storage, value storage, and valid. Now, obviously, this can fail now. So we're hoping that this stuff looks like, just that we can like initialize this thing without like falling the fuck over. And I guess that the number of elements is like kind of sane. Just like ballpark. Map, key storage, length. Let's just take a look. Right, this hash function doesn't exist yet. Okay, so we got 21 elements. Does that feel about right? So we have our key type is 8 bytes long, plus 8 bytes of pointer length, which is also 8. So we're like an order of magnitude off, no? 21 is like totally fucking wrong. So we did something fucking stupid here. Let's make sure the math is right again. So we have key size times n plus value size times n plus n over 8 is equal to buff length. That, I believe, is true. Right? Cool. So then we multiply both sides by 8. 8 times key size times... Can we just... Yeah, 8 times key size times n plus value size times 8 times n plus n is equal to 8 times buff len. Yes. Then to get n, we factor it out here. So n times 8 times key size plus 8 times value size plus 1 is equal to 8 times buff len. Oh, I forgot the 8. Yeah, you're right. I did just forget the 8. Oopies. Thank you. 169. Okay, is that more sane? 169. One. Okay. 169. Jesus Christ. 169 times 8 for the keys plus 169 times. Oh my god. 169 times 8. Jesus Christ. Get me out of here. 169 times. Okay, fuck it. 168 times 8 plus 168 times 8 again. It still feels a little wrong. Let's try again. 169 times 8 plus 169 times 8 for the keys and values plus 169 over 8? Yeah, it feels wrong. So let's double check this again. Okay, 8n. Well, let's start with the original. Key size times n plus value size times n plus 1 over 8 is equal to buff len. Then we multiply 8, so 8n, 1 over 8. Fuck. N times this. Key size, value size, n times 1/8. Buff len. Multiply by 8. 8 times buff len. 1 over 8 cancels out. 8n, 8n. Then we factor out the n, so it's n times 8, key 8 value plus 1 equals 8. N equals 8 times buffline over that shit. So that seems right. So what am I missing? What am I missing? You're right, Python is nice for this. Dude, this is not supposed to be where all of the time in this stream is going. This is not supposed to be where it went. 8 times 169 plus 8 times 169 plus 169 over 8, right? Okay, that's the right number. So now let's do it the other way. 8 times 4096 over 8 times 409 times 8 plus 8 times 8 plus 1. 254. Okay, so it looks like we're just doing this wrong, right? Because buffline is clearly, yeah, this is not the same number. 254 makes way more sense, right? We do this with 254, and we get just under 4096. So that's right. That's the right answer. So this math is like sane. It's more our implementation of this thing in Zigland is not right. If we take, I assume that it's not this, right? Let's print these values and see if they're what we expect. This could be the problem, right? Buffland, keys, size, and value size might just be not what I thought they were. Oh, of course, because the value size is 16, because it's 2 pointers. Ah. Okay, so does that make this correct then? This math is, we say 8 times 169 for the keys, 16 times 169 for the values. Okay. I'll take it. I was wrong. I was wrong. Okay, that's sick. That's sick. It's kind of nice when the math is right and you're wrong. Okay, so this is the correct size. This is the correct size. So now I guess we need to, I guess we said at some point we did pre-allocate, which was hard because I'm a dumbass. And I guess now we try to insert something into the map, right? So I guess we'll call this insert. So let's start with a really fucking dumbass hashing function, right? Let's say that you want what are some nice properties of a hashing function? Like relatively random, probably, and relatively uniform. We can kind of say that we won't be relatively random if we just do a mod of the length, but I think that we'll start there. So let's say we have a key. We have key is a type, and we're gonna have the key is a thing of key. I guess maybe we just can write keys any type. And we return a usize. And we probably say like max like num elms, right? Or like capacity. So let's just do key over modulo capacity. Easy. World's simplest hashing function. We'll come back to this later. I think that like the chance of me designing a good hashing function are like pretty much 0. So we'll probably just steal someone else's later. But for now, we'll just do this. And this will make it also like there's nice properties about this that means it's easy for us to like test our collision behavior and stuff, which is kind of nice. Okay, so let's do hash key. And I guess we just say self valid. Is there like what is the fucking interface on dynamic bit set? There's got to be like a get. Is set, I guess is what we're asking. So we're looking at is set of index is hash key. And key storage len, right? I guess technically we can cheat here. Theoretically, fix me, we're storing too many lengths, right? Really, like, the key storage should be a pointer, value storage should be a pointer, and valid, we are gonna have to, like, get into this dynamic bit set and figure out how to, like, fix that as well. But for now, we'll just do it the stupid way, where we're, you know, a few extra wasted bytes. A few extra wasted bytes, it's fine. We'll live. So we say valid is if this is set. Okay. And if it's not valid, unreachable. Right? Because we're dumb, stupid fucking idiots. And otherwise we just say key storage at index is equal to key and value storage at index is equal to value. It's the world's simplest implementation. In a former workplace, I found a self-built hash function in a security-related part, and it was just an XOR of bytes. Yeah, that's a fucking classic. The classic XOR is encryption. And then for get, I guess it's just like, I guess it means that we're probably gonna want like a helper function. That takes key and returns a usize. And this is just like hash key, return this with the correct self key storage length here, which means that we can just go easy calc index, boom. And then we can kind of do this here as well. And here we want to check if it's valid again. And if it's not valid, this is return null, easy. And that means that we just return value storage at index. And it seems pretty clear here that this is like get or put is a natural interface here to deduplicate with get. But for now, we just do it like this. For now. So I wonder if this will just work now. No modulo i64 new size. Okay, fine. Incompatible types i64 new size. Yeah, true. How can I fix this? I guess we just try to cast key to a usize. Which doesn't really work. We probably try to bitcast to the unsigned version, then upcast to a usize. So type info on key probably. And we'll say we only support ints for now. But on here we can say int info. If info signedness, maybe we switch on this. We bitcast this to the equivalent size unsigned. I think. So how do I use this? I probably need to do like unsigned type is a type int is equal to like this. So get like the equivalent unsigned type, and then we do like bitcast unsigned of key? Jesus. I guess. And then this gets the like, we just break out unsigned. That seems kind of reasonable. I think it's like this, actually. And then for unsigned, we just like break block key. Yeah. Yeah. Key unsigned is this. There was probably like a std meta function for this or something, but I didn't think about that until right now. And then we do key unsigned. And now that should work fine. Yes, so that builds. So now when we put 10, he's mad. Oops, if valid, it's unreachable, actually. If it's invalid, we're kind of chilling. Right, so we kind of do this. So we actually made it all the way here, which is hype. So we get the string at 5 and the string at 10. And we can do like std debug print. The string we got in index 5 should just be the number 5. You know? It's pissed because, or else unreachable. Unwrap the string. Look at that, baby! Look at that! We basically run a hash map. It's basically done. Right? There's nothing that could go wrong here. So, let's, if we try to put now, we try to put, map dot value storage dot len plus 5, you know, colliding. Collide. We assume that this will crash now, I believe. I believe this crashes, yeah. Right, so now we hit the fucking actual part that makes a hash map very, just like at all interesting at all. So let's do some sort of collision resolution. So now obviously get and put, they're gonna have to share collision resolution. So I think all of this goes into calc index. It must. So I think calc index doesn't just return a usize anymore. I think this also returns if it's valid. If this is like valid already, and the index. Because there's no world where we want this thing, we don't care about that. I think. We'll see though. So we say like, you know, I guess we store like this thing as a variable thing like this. And then we can just go like, oopsies, what the fuck did I just do? Get me out of there, okay. While, so at this point, say we look this thing up. How do we know if it is a collision or not? That's something that we need to like figure out. So I guess it's like, if the key at that place is the thing and it's valid. So I guess we first check if it's valid. So if it's not valid, we do something. Self valid get index, right? If it's not valid, I think that we're just chilling. I think. Let's think for a second. Yes. If it's not valid. Dude, my brain. It's melting. It's fucking melting. Return index is index. Valid is false. Right? Why is this failing? What the fuck? What doesn't it like? No function named get. Oh, I see. Is set. My bad. My bad. I'm realizing right now that there are problems with removal in the future. But I can I just write it down and then not think about it? Removal means there will be holes, and we need to skip invalid but previously set elements or something. Okay, but in that, ignore removal for now. Ignore removal. So next we just increment index. Oh, next we have to check the key. So existing key is key storage at the index. If existing key is equal to the key, return this guy, right? That's hype. Otherwise, we just keep going, right? So that makes sense so far. We just move forward until we run out of space. And so that means, like, we probably are going to limit this to looping over the whole fucking map, right? For 0 to self key storage len or something. And then we need to do index is index equal to index plus 1 modulo the buff length. Right? So now we will only ever try to rip through the whole list once, and if we don't find anything, then we're fucked. And so then we return error out of memory. Or maybe this is return null, and then we convert that into an error in the places where it's relevant. Okay. Now, does that mean that every time we look up, we're missing something here, where if it's invalid, oh yeah, if it's invalid, we always return true. But if we hit only valid elements, we hit all valid elements and we'll go through the whole thing. Okay, cool. Cool. So now we kind of change these to look like this. Why is this mad? Oh, or else return error out of memory. Something like this. And then this is if or else return null if we can find anything. Yes. Yes. I think that makes sense. Let's test. So we can still get we still get 169 elements, we still can get 5, and we can probably still get 10. Let's just check that we get 10 as well, and then we'll try punching in a number that isn't either of those. Oh, I guess we should test this value as well, to make sure that collision getter works as well. Which this can be an incast, I guess. Okay. So that's really good. We get the thing at 5, we get the thing at 10, and we get the thing at collision. So that, shockingly, we're done. We're done. There's nothing else to do here. So I guess let's try to make sure that we can test, like, more robust test. Okay? So can we do something like create a list of numbers that's like too many, right? So we think that there should be 169 elements that can fit in. I would love to allocate like 169 unique numbers that are like likely to collide, that have collisions in them. That's like a thing that we want to do. So I think we intentionally make some collisions and see what happens there. So we probably want to like, does order of insertion matter right now? I don't think so. So can we just go like to insert is going to be a list of 169 I64s. Yes. For 0 to 169, we're gonna do no to this. That divides nicely, I think. We say map put I, and we're gonna put the number in here. So we're gonna do num is equal to stub try stud format buff print alloc print, I guess, in some allocator that we don't have yet. The number and the number, boom. So we're gonna be like formatted is formatted like this. Okay. Now we're gonna do this 3 times, but each with like 2 insert is equal to I plus 169 because we know that's gonna collide here, right? And here as well, right? So just the same thing. Yep. And now we need an allocator that we can work with. So var scratch buff doesn't really fucking matter. Var fixed buffer allocator is stood heap fixed buffer allocator, initialize with the scratch buffer. I assume this is enough, but if it's not, get fucked. To insert val. And I guess really we don't need this buffer here. Yeah, nice. Int cast, I guess, here. In all of these. Okay. Okay. Now, I guess we loop through all of these numbers again and hope that we get the right value back at the end. Right? That seems reasonable. I think that makes sense. So here we go get I, and we're saying like stood testing expect equal strings of formatted and this. Okay. And on these we're doing map get. Okay. Yeah. And these aren't try. This is just like this. That seems reasonable. And we'll see if we'll bump the memory if we ran out, which we might have. Expected type constituate found this. Oh yeah, sure. Or else unreachable. Get fucked. Yeah, there we go. Nice. Noise. Okay. Yeah, these, everywhere we wrote S here has to be D for number. D for denumber. Of course. If something collides at the end of the memory range, does it wrap? It should, yes. That's what this is supposed to do. But I might have got it wrong. You never know. I don't. Expected this output, instead found this. Okay, so that's interesting. That means that we did something fucking stupid. Nice. So can we print on each of these the number that we're on? So it's literally like the first fucking index. We're fucking this up. That's crazy. What the fuck? Did we really fuck it up that bad? That's kind of funny. Okay, so can we inspect key storage then? So we should be looking at like what's in key storage at 0, index 0. Which is 0. Like, right, that makes sense. So why is he expecting 169? Let's print here. We're going like first, second, and third. So I'm assuming this is crashing on second, right? Oopsies. Right, he's getting through the first one. He's finding the 0 at index 0, and then he's trying to add 169, and then it's still showing 0, right? Which means that the getter here on calc index is returning the wrong index, right? So the question is why? If existing key is equal to key, return this. So this must be returning true. Can we maybe say here, putting key value into key, right? Let's just, and by key, let's also put the index. Right? Let's just see what's going on here. So putting 0 into 0, 169 into 169 at index 1, and 338 into this, right? Oh, we're actually kind of hitting like the fucking worst case of this, by the way. That's kind of funny, because now 1 wanted to go into 1, but it's like double colliding, so we're actually kind of making like the worst fucking possible hash map ever right now, which is very funny. That's very funny. Because it means that like this guy, 55, is iterating for all the way from 55 to 165 here. This is an awful collision case, which is very awesome. Okay, so, but it looks like on put we're doing the right thing, right? So that means you're not starting at the hash index. Well, the hash index is the world's stupidest hash function. It's literally just this. So when we end up with a better hash, it should probably do something better. But our hash is fucking brain dead right now. So yes. So it's the getter that's losing his fucking mind. So why? Let's just like start here by doing getting key at this. Let's figure out why the fuck we fucked this up. Key index. So getting 0, second getting 0. Whoa, okay, whoa, chill. Oh, I'm just fucking stupid. I'm just getting I every time. There's actually nothing wrong with the map. It's actually just my logic. In calc index, you're just iterating and returns the first available. It's not. It's returning. It's starting. Well, yeah, I guess. Yes. The answer is yes. Because it's assuming no removal right now, which we'll have to fix. Oh yeah, I guess on get, we can't. If it's invalid, we can't do this. Huh. Allow empty. Allow invalid. If not valid and allow invalid. So on get, this should be false, and on put, this should be true. But we didn't actually have, we need like a case to hit that. But you are right that that is fucking stupid. So can we bring that bug back for a second and try to find a way to trigger it? Maybe if we use, right, because right now this will work fine. But we need a way, cause it's because like the way that we put this stuff in is very clean. It would maybe make sense to put in random numbers, just like fully fucking random numbers. And then I think that this, wait, hold on. This would fail if we tried to get a number that didn't exist yet. That's where this falls over. So this bug would happen if here, just we tried to get from I plus 1 here. I think that this would fall over. And actually we're expecting null on all of these guys because they don't exist yet. Yes. Yes, 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 yes. Yeah. So we're here, we're saying, get me the next thing, and it shouldn't fucking exist. Oh. That's annoying. What the oh. Can we just do expect equal then? Does that kind of fix this? Yes. There we go. So now he's like, I expected null, but I found something. And we're like, yo, what the fuck? Then we go back into get and we say allow valid false or allow invalid false. Expected null found. So this is still wrong. Oh, because I plus 1 here. I'm a dumbass. I'm just doing the wrong fucking test. There we go. So we go back here. We put true in here, which is what we were doing before. This will fail. The fuck? What the fuck? Why? This shouldn't work. Because if we try to get I plus 1, it's going to iterate. It's going to be like, I found. It will eventually find an invalid slot. Oh, but we were handling this here. Which is interesting. So the failure comes from if there's a hole. No, it would have just worked. It would have just been fine, I think. No, it would have returned. It's if we had the thing, but it iterated and there was a hole, which I'm not sure if it is a bug case, to be honest. I'm not sure. But this is like safer, so we'll just do it this way. I'm happy with this. Okay. So we have this. Now, what is the next thing to do is to handle removal, right? Removal is the scary part. Because as soon as we remove something, it means that this like logic of iterating forwards no longer does what we expect, right? Because if we're like, I have thing here, but like it's not what you wanted, then you like move forwards where all of these things are full, right? 1, 2, 3 things. And you like put the thing you wanted here because this is like where it fit. Then you like remove this. Like, how does this, now you like never make it here, right? Because you get to this guy and you go, sick, dude. There's some space here. So it's almost like you have to, on removal, like figure out who needs to be moved backwards, or flag in some way that you should keep iterating even though you could put something here. Which I think works, right? So you go, if you're iterating forwards and you're looking for somewhere to place, you're looking for somewhere to place. This guy goes on, he goes, oh, on put, I'll put him here, right? But on get, he goes, uh-oh, this is usable, but has been used in the past. Then he keeps going. Yes. I think that makes sense. So, how is... Are those... That's 2 bits of info? It has to be, right? It has to be. Yeah. Which we can just kind of do like this. Skip on get. Yeah. Yeah. Which means that this math needs to change. So this is 2 over 8 here. 2 over 8 here. Which means that this is 2n. Which means that this is 2. And this is 2. So this just becomes 2. Okay. Which means that now the number of things that we can store is going to change, which is fine. We just have to be careful about how we do this stuff. So this is going to be skip on get. Which is going to be false. Like this. Usually you have a probe order and route, Robinhood style hash maps, and some others you shift for the rest of the order. Which are the deleted slots? You skip those. In both cases, you hit empty. And you were done. Yeah, that makes sense. That makes sense. I'm gonna do the stupidest thing first, though. And then we can improve later. I think, wait, what did you say? Usually you have a probe order, which we have, right? We're just doing linear forwards. Robinhood style hash maps, which I assume is what we're doing. Some others, you shift the rest of the order for tombstones, which are deleted slots. You skip tombstones. In both cases, you hit empty. You are done. I'm not sure I understand. But I think... Yeah, I don't think I understand, but I'm sure what you're saying makes sense. I'm just not there yet. Okay. So, skip on get here. I guess it's set here. No, maybe it's set on removal, huh? Yeah. So here we're gonna be like... Key is key. And I guess we say like const index is calc index key false, or else return. So we're here, we're saying, let me find if this thing exists. Self valid at index is that, how the fuck do you clear something on this fucking dynamic bit set? Changes the value to this bit. Oh, okay, so there's onset index. Okay, and then skip on get, which you were calling tombstones. We set. Oh yeah. I don't start on 0. True. I start at whatever like the hash was and then move forwards, which is slightly different, but same idea. I understand. Key storage. I guess we don't technically have to clear these things, but we could say key storage index is equal to undefined, just for like memory safety stuff. And this will get compiled out in debug builds, or sorry, release builds. Seems reasonable to me. And so I guess, interestingly, I think that skip on get maybe just never gets cleared. because you don't know who used that information. You can like try to track that somewhere, but it's probably easier to just leave it forever. In which case, it's actually possible that just you should always loop through the whole thing. Maybe. It depends on like probably not. It depends on like how painful this gets. But we'll see. Okay. Sure. Fuck it. I mean, over time, this will just get bad. But maybe that's fine. So now we have to make sure that, like, skip on get is self skip on get is set index. And so if not skip on get and this, I guess if allow invalid, this is like a fix me, allow invalid is more like I'm calling this from put. Yes, that's kind of more what this is like. Moving other valid entries backwards has two advantages, right? You amortize the cost to single removal instead of a subsequent lookup. Yeah, that does seem... I was thinking that moving things backwards is painful in some way, because you might move things that you have to know if the thing you're moving back, like how far back it wants to be moved, if that makes sense, which is maybe fine, right? I was thinking that like you don't know if like this guy you don't know, I was gonna say you don't know how far back this guy wants to be moved, but you do if you just calculate the hash, which you can do. So you just say like when I move forward, I loop the whole fucking array and move things back. Yeah, the logic there is tricky. I think you have to iterate the entire fucking hash map and move everything back that would want to be moved back. I guess only through valid indexes, maybe, if you did it that way. Yeah, you could probably get away with that, where you say, go forwards until you find a hole, and just move things backwards if they want to be moved backwards. Where want to get moved backwards is like, if the hash is greater than the current position or something. I think that would work. But I'm going to do it this way instead, because this is like makes more sense to me. The reason you have tombstones is because you have multiple probe sequences to distinguish between a disturbed subsequence. You might move something too far back. It will work right now, but only because the entire table is scanned. Yeah, true. Yeah, I'd have to think about it a little more. I think it's possible, and I think it's like not trivial. I think surely there's a way to like to like clean up the whole map. There's got to be a way to be like clean up and like put everything more where it wants to be after removal, but I'll just skip that for now. Okay, so if we are skip on getting, when does this come into play? So I think skip on get hold on. So when we're iterating these things, even on put, we still need to keep looking. Dude, is that just fucked? So like I'm here. I go boom, hash brings me to here. And if this is like not what I want, I like move forward, and as soon as I start moving forward, it's like if anything has ever been in this slot ever, then I have to keep looking. I have to. So it's almost like the checking for the next invalid slot for placement is different than than checking if the thing exists. Yes. Okay. No, that makes sense. So it's almost like this calc index should return first invalid, like it should be like either I found something or I didn't find something and here is where you should go. That's kind of like the two cases, I think. Right? And so when we're doing a put, we have to make sure the I found something case didn't happen. Yes. And then if this doesn't happen, then we just write down the first invalid index. Yeah. So, first invalid is going to be null. Then as we work forwards, instead of returning here, we just say first invalid is equal to index. If first invalid is equal to null, right? But we have to keep going to check if the thing that was there is there. So then we check the skip on get value. If it's invalid, okay, if the thing is invalid, if it's valid, we know we have to skip. If it's not the right thing. If valid, this is when we do the existing key check. So that's kind of simple here. If it's not valid, which is now just happening, then we try to set the first invalid, and then we check skip on get. Yes, okay. So if skip on get, then we keep going. If not skip on get, then we are done. And if we are done, we return this. So if first invalid index, first invalid index, then we return found something. So this is going to return, like, I almost feel like this should be like a index is a union. I feel like this is just kind of how it's making sense in my brain. So existing at some index, right? Or empty, and this is a, I guess, also a usize. So this is like an existing slot, available slot, or missing, or like not found. Is that true? Is that what I want? I guess so. Maybe. We'll see. Okay. So that means that, like, this is an index. And if first invalid, we return. So here is like we found it. So this is return existing is equal to index. Yes. Okay. if it was valid and we found it. Otherwise, at here we're fine. We say return available at first invalid index. Yes. Otherwise, we return not found. Okay, that seems kind of reasonable to me. That seems pretty reasonable. So now these guys have to change, right? So this is a switch here. So here if we found like existing or available, it's like here is the index. Else return error out of memory. I guess really we should be saying like not found. Okay. Okay. And then I guess technically these things are actually going to behave a little bit differently, right? So if it's existing, then we only have to set the value. But if it's available, then we have to set all three. Yeah. Interesting. That seems like it's kind of working. Okay. And I guess to me it seems reasonable to set this now. That's how it feels reasonable to me, just looking at this. Okay. Now, this guy, when we call calc index here, we need to switch on him now, on get. So, on get, it's like, if it's existing, we're chilling. Otherwise, we return null. If it's available, it doesn't count. And then on remove, it's oops. On remove, we go switch self-calc index key. If it's available or not found, we have nothing to do. Otherwise, it's existing and we have to remove it. We have to clear it. So it's like, so we do this stuff. Okay. This seems kind of reasonable. I don't know why he's not happy here. It's shadows. Oh, I see. Okay. Okay. So I guess let's just look and see if the existing tests are working okay. They're not. 216. So what's going on here? Let's see. We're getting here, we're on 2 insert is 169. And he's saying, I did not find 169. Okay. Why not? Why not? Let's go back to this. Let's go back to the test here where we write down where everything is going. Inserting this at this. So this is key at index and replacing. Let's just start here. Does everything still kind of work? So we're putting 169 at 1, inserting 1 at 1. Okay, so this is bugged, right? 169 should be like I collided with 1 should be like I collided with 169. So why is he not doing that? It means that this is returning existing. Or does it? No, he's saying inserting. So he is getting to this available, which means that he's getting down to the bottom here, which means that he had first invalid index set, which is, oh, else if here. Oopsies. Oopsies, I'm a dumbass. There we go, this is working now. This is working now. Okay. What's going on here? There we go. Why is this being like this? Whatever. We'll scroll and then it'll fix itself. Okay. So now we need to test removal. Removal is the scary piece here. So can we just kind of randomly remove shit and see what works? Just make sure that like everything else is consistent. So do we have a random number generator here? Let's just do like shuffle. Do they have something like that? Fill. Oh, sorry, random here. Oopsies. You need the random interface. Do they have a shuffle? Yeah, they do. Let's go, baby. So let's shuffle a list of inserted indexes, which we can actually do by just cloning the key storage, I think. Because this thing should be full, except it's not because 169... I would think that 169 doesn't fit anymore. Oh, it does. Okay, sure. So maybe here we say like inserted is maybe like this. Alec, one of these. So we have, oh, my brain, dude, it doesn't work. Everything hurts. 169 is how many of these things we're doing. Right, and then we're doing inserted I is equal to I. This needs to be tried. Inserted, which I spelt wrong here. This needs to be a int cast, and then here we do inserted I is equal to insert, and this is I plus 1, I times 3, I guess. And then I times 6. I think that works. I think. So then we should be able to be like random shuffle inserted. This is unhappy. Why? Because he needs the type here probably, right? Yeah. And I guess we want to make sure that like, oh my god, random, we need like some way to like look at all of these things in order, in some random order, remove some element, and then shuffle it again. Yes. Yes. So I think it actually makes more sense if this is a, this is nicer as a runtime bounded array that we allocate up front with 169. Okay. This just makes things easier. Then we can, in here, we just write like inserted dot push append. Okay, to insert. Okay, easy peasy. And then what we'll do is we'll just pop one every time. So we'll go while, or like for 0 to 169, for how many things we have, we shuffle the inserted things. We pop the back one. So we say, inserted pop or null, or else unreachable, or else break. This becomes while true. Since when were you playing Smashing Pumpkins over Taylor Swift? I don't think I was I? This is just the Smashing Pumpkins, no? I don't think there's any Taylor Swift involved. Okay, so we pop or null, we get the last thing, and then we remove that from the list. Yes. And can we make sure also that we have removed? Oh, yeah. So then we track the number of removed elements, and we just say like map remove this thing that we just took out, this index, and then we say removed append last, and then we just want to make sure that like for each element in inserted items, if we want to do like a map get on this thing. So you get this thing. Yeah. And we're assuming that these things exist. So we're expecting this to be stud format buff print into some buffer with the number of this index. Okay, so that's this. And this is or else unreachable, because this thing has to be in there. And then here we need like is buff a thing that exists? If so, that's a problem. We'll make sure. Okay. Then we also go over all the removed elements, and we expect that these are null. Yeah. That looks kind of nice. And then this should break when we are out. That'd be kind of hype if this worked. Int cast on these. Okay. While true. Oh yeah, this is now like this. Let's see. Does that fucking work? Holy shit, we're gods. We're gods. Look at that. Right? Boom, it doesn't crash, dude. Doesn't crash. I think. Yeah, so we can say, we'll just make sure. Testing missing of this guy. Missing ID. And we're testing this still there. I would say that's a success. It's at least happening. That's kind of sick. Cool. So there's obviously like more to do here, right? There's like iteration of the list, which I guess we could just rip the whole list and like skip any empty segments. We've kind of like made the problem a lot easier by not having like capacity, right? So usually I think that you would kind of keep everything close together and you would like expand memory over and over again, but because we just didn't do that, it kind of makes the problem easier. Maybe we do want to do that later, We need to pick a better hash function. I think we can just replace this, by the way, with like stud hash auto. Like, there's like this thing, I think is what they use. So I think they have like in the standard library, they use like a hasher context, which we might just be able to like kind of abuse here. Auto hash map. Right, this guy has auto context here that has hash and equal. Right, so we can probably like cheat here, and we can probably say that hash is like here we can do like stud hash map auto context or something. No, where does this thing live? Stud hash map auto context. No, yeah, right, we can kind of cheat and do this. Auto context key. I don't know how this thing is like constructed though. How the fuck do you construct this thing? Auto context. Hello? So what do they do with this guy? They have just context here? They have context as a context. How do they initialize him? Oh, I see. This thing is empty, so it's fine. Yeah. So what do? They set like void or something. If the size is 0, then they just write CTX undefined. Sure, we can do that. Nice. Look at us go. And then for hash, when we call hash now, it's just like type of self context hash, or it's like self CTX hash with the key. Right? This should, like, what does this return? It returns a U64. So here we have to probably modulo this ourselves. Right? But this should do like effectively the same thing, I think. And now we should just have like, right? So this thing still worked, but we just have like more sane hashes now, right? Which is kind of sick. So what else would we have to do? We have to fix the hash function, do like bake better interfaces, iterators, getter put, all that jazz. It would be nice to like test how often we're like iterating. We should probably do that now too, right? So we should say var skip count is equal to 0. Skip count plus equals 1. And can we just like stud debug like let's do global is like this, and we have like skip count is like this. I guess we just do this. Kind of like this. Yeah. And then we can kind of see like how many times we skipped total. Like this. Yeah, so we're doing a lot of skipping. Like a lot, which is probably not great. Interesting. So there's something there. Maybe what we can do is actually do this. put this here and just log how many times it happened at the end. Let's do that. That will look a little nicer. All right, we'll just kind of put this at the very end. So with the better hash, we've wasted 2 million skips, which is not ideal at all. But let's look at if we use like our uber shitty skip our hash function, right? I assume this is worse, unless we've done something really fucking dumb here. Let's see, self value storage or key storage len. Surprisingly, this is 3 million, which is like worse, but not as much worse as I thought. I'd be kind of curious to see if we make the buffer that we're using here like a lot bigger, like 1 meg. Give him like a, oh, that's the wrong buffer. So let's like give this guy like 1 meg of hash map storage, right? I'm assuming that now this should be relatively small. Here we're at 300,000 on our shitty version, but what about on their version? Do we get better if we use like a real hasher? 300,000 down to 14,000, yeah. So when there's more space, the amount of skips we have to do gets a lot smaller, which makes sense. Yeah, I think that's like an okay spot to call it here. So we have like the world's shittiest hash map. It's probably not very performant. Our collision resolution is like relatively stupid. We just kind of like move forwards and see if we have like put something there before. At the very least, though, the interface seems to be working correctly, which is really the main thing, right? We can always improve it later, but at the very least, like we're not seeing anything blatantly stupid. And all this thing is really like a hash function plus a couple bits of metadata, whether or not this thing is valid and whether or not we can skip it, or whether or not we like have ever put something there. And all we do is we just like kind of say, uh-oh, something's in the way, move forwards. I'm sure there's a better way, but this is good enough for now. Thanks for watching, guys. If you like what we saw, we stream most days, 12:30 o'clock to 4 o'clock Pacific time. It is 4 o'clock Pacific time now, so anywhere between 3.5 hours ago and now, if you're watching live, is when you should expect to see us. We've been working a little bit on like a little bit of a web app to do meal tracking, as well as an Xbox controller that we're building from scratch. I'm hoping to get back on this guy soon, but we've got like some like PCBs ready to be, or almost ready to be shipped off, as well as like some like hardware that we've printed. And some firmware we've been working on. So we'll get back on that one after we finish the meal tracker. If you're watching live, this VOD, we're going to split today's stream into 2 VODs that will go on the main YouTube, which is linked in the Twitch description. If you want to see, projects that we're working on, you can keep up there. Sometimes we will do stuff that is not worth posting there, whether it's because like the algorithm doesn't like it, or that's actually really the main thing. If the algorithm doesn't like it, we don't post there, and instead we post on Patreon or on YouTube member segments. So if you want access to all VODs, whether or not YouTube will push them to you, you can support in those areas. Yeah, please consider supporting. The stream is going to end when I run out of money. I will be clear, I am running, like, the money is going downwards, not upwards, right? So eventually I'll run out and I'll have to get a job. So every dollar that I make doing this extends the lifetime of this by some amount because I'll run out of money slower, right? So if you guys want to continue this to continue, consider supporting. But that's, obviously no pressure. I think that's all the plugging I feel like doing. YouTube, peace out, and Twitch, let's find someone to raid. Just post the VODs on OnlyFans. Perfect.